Hi, my name is Bruce Bouquet, and I'm from the New Jersey Institute of Technology. Welcome to Numerical Methods, how to use computers to solve difficult math problems. In today's episode, we'll consider polynomial interpolation. Previously, we considered Taylor polynomials. In that case, we knew the form of a function, and we knew its value at a point, and we were able to compute the derivatives at that point, as many derivatives as we wanted, and from that we would try to approximate function values at other points. But suppose we don't have the form of the function. Suppose we only know the values of a function at certain points. You might consider, temperature at certain times during the day, and you want to fit some sort of smooth curve through those points. So can we approximate the values of the function at points other than the places where we know them? Well, the first thing you might try is linear interpolation. We can use piecewise linear functions and just connect the points with line segments. If we have 2 points, x0, y0, and x1, y1, the usual way to do that is to write y minus the y value is equal to the slope times x minus the x value. We could use either of the points. We could just as well have used x0, y0 in this equation. This equation can also be written in the form x minus x1 over x0 minus x1 times y0 plus x minus x0 over x1 minus x0 times y1. One can work it out and see that these equations are equivalent. However, in this second form, it's going to be easier as we go ahead to form a systematic way to deal with higher order polynomials. Let's just consider a simple example, the line through 1, 1, and 2, 4. Well, we can plug in x1, y1 is 2, 4. So wherever we have an x1, we plug in a 2. And wherever we have the y1 over here, we plug in the 4. For the x0, we plug in the 1. For the y0, we plug in this 1. And we get the line through the 2 points, 1, 1, and 2, 4. And there's only a unique line through any 2 points. So if we plug in over here, let's say x equals 2, we see this part goes to 0. The 2 minus 1 over 2 minus 1 goes away, and we just have 4. If we plug in 1, 1, this second piece goes to 0 because you get 1 minus 1 equals 0. And 1 minus 2 over 1 minus 2 cancels, and you just get 1. So when x equals 1, you get 1, 1. Clearly, this is a linear function, and it goes through the 2 points, so it must be the same line. If we used this line to approximate the function value at 3/2, we just plug in x equals 3/2, and we'd get minus 1/2 over minus 1 times 1, which is a half, and 1/2 divided by 1 times 4, which is 2, and we'd get 5/2. Well, we know 2 points determine a unique line, and one way to show that is to solve the equations. ax0 plus b is y0, ax1 plus b is y1, and as long as the determinant is non-zero, you get a unique line. One can also do the same thing for a quadratic and higher order equations, higher degree polynomials, and we can see we can get a unique quadratic when we have 3 points, and solving these equations gets messier and messier as we use more and more points. To prove it, that there is a unique quadratic through 3 points, one can suppose that there are 2 quadratics that go through the same 3 points. Call one of them p of x, call the other one q of x, and if they pass through the same 3 points and they are quadratic functions, you can subtract them to get at most a quadratic. Let's call it r of x, where r at x0, r at x1, and r at x2, since they go through those 3 points, when we subtract p minus q, the function r of x is equal to 0 at those 3 points. But if a polynomial is equal to 0 at a point, then there must be a factor of x minus that x value. And so we must have our polynomial x minus x0 times x minus x1 times x minus x2, possibly times other polynomial pieces, Well, that's no longer a quadratic. That's at least a cubic. And therefore, there is no quadratic function r that can satisfy these equations. And therefore, the supposition that there were two quadratics has been contradicted. And so there can only be one quadratic through a given 3 points. If you're using n plus 1 points, then that would give you an nth degree polynomial. 2 points for a first degree polynomial, 3 points for a second degree, 4 points for a cubic, etc. As you use more points and get higher order polynomials, it becomes harder, it becomes messy. The functions become sensitive to small errors as you add more points. So there are problems with using higher degree polynomials, but we're going to show you how to do that anyway, at least to start. And we're going to use Lagrange polynomials. And what the idea is that we can construct polynomials of an appropriate degree. So if we had 3 points, we would have quadratics. If we had 4 points, we would have cubics. And these polynomials will have the special property that these polynomials will equal 1 at one of the particular x values and equal 0 at all the others. And then we will make a polynomial that's equal to 1 at another one of the x values, whereas at all the other x values, that polynomial will be equal to 0. And we do that for each of the points. And here's the case for the quadratic. Let's take what we call L sub 0 of x. We can notice that if we plug in x equal x0, that everything cancels out and we just get 1. Whereas if we plug in x1 or x2, L0 is equal to 0. Similarly, at x1, if we plug in x1 for x, everything cancels out and we get L1 of x1 is 1. Similarly, if we plug in x0 or x2, L1 of x will be 0 at x0 and x2, and similarly for L2 of x. And therefore, we can write the quadratic polynomial through 3 points, x0, y0, x1, y1, x2, y2, as the sum of these 3 functions. That this function is equal to 1 at x0, so it would be 1 times y0 there. The middle piece, well, that's equal to 1 at x1, and so we multiply by y1, and so our polynomial will equal to y1 at x1. And at x2, the first 2 polynomials will be 0, but the third polynomial at x2 will equal 1, and so you get 1 times y2. So one can easily see that this polynomial will go through the 3 points x0, y0, x1, y1, and x2, y2, and therefore it must be the unique quadratic polynomial through those 3 points. In general, if you had n plus 1 points, x0 through xn, 1 in the numerator, all you do is you take x minus each of the points except for the one that you're interested in. So L sub I of x would leave out the x minus xi term. And in the denominator, you have xi minus x0, xi minus x1, etc. And again, you'd leave out xi minus xi. You don't want 0 in the denominator. And that will give you all the L's. And so Li of xj is equal to 0. At all the other points, Li of xi is equal to 1, and then your polynomial is simply the y values multiplied by the appropriate one of the polynomials that you have. Problem with this is that if you add more points, suppose you did this process and you had 4 points and you found the cubic Lagrange polynomial, and then you found a 5th point, and now you want the 4th degree Lagrange polynomial. Well, you'd basically have to start all over again, because then you'd need to construct all your 4th degree polynomials, and so that would take a lot more work. Using polynomials, one might ask, well, why do we want to do this? Polynomials are easy to evaluate, they're easy to differentiate, to integrate, and manipulate. Polynomials are smooth, at least piecewise. We can have them smooth, or if they go through all the points, they're surely smooth. They have derivatives of all orders. But higher order polynomials oscillate wildly, and there is a lot of sensitivity. In order to construct these Lagrange polynomials in a more straightforward way and in a way that enables us to use our earlier work as we build up higher degree polynomials. We can use the concept of Newton's divided differences, and these look kind of like derivatives. We say f of bracket x0, x1 is just the slope of the secant line connecting those 2 points, so that's approximately the derivative of the function. And then if we have more than 2 points in our bracket, what we do is we take the rightmost. If we have 3 points, we take the right 2 minus the Newton's divided difference with the left 2 and divide by the last number minus the first number. And then from these pieces, the f of x1 comma x2, we use the previous format. And we can continue doing it that way. If we had x0, x1, x2, x3, we'd take the 3 right numbers. If we have 4 numbers in the brackets, then we take the 3 on the right minus with the 3 on the left, and we'd work our way down. And it can be shown that the Newton's divided difference with 2 points is like a first derivative. The one with 3 points is like a second derivative over 2 factorial. The one with 4 points is like a third derivative over 3 factorial. So very similar to the look of our Taylor series. And if we had n plus 1 points, then that would give us the nth derivative at a point somewhere on the interval between x0 and xn, assuming x0 is less than x1, less than x2, etc., divided by n factorial. How can we use that? Well, we'll have our helpers, Aviva and Elisheva, work this example for us. And what we do in order to compute these divided differences is we take the function value minus the other function value. Here we take 3 minus 0 divided by 0 minus 1, the change in f divided by the change in x, to get our divided difference. 3 minus 3 divided by 2 minus 0 is equal to 0. Notice the points do not have to be equispaced. 12 minus 3 divided by 3 minus 2 gives us 9. So that's the first divided differences for the function through these 4 points. The second divided differences are found by now just taking the difference of the previous ones. 0 minus 3 divided by 2 minus negative 1. We go to where we found our values from. So the 0 is found from on the bottom as low as you go on this chart to the 2. This 3 up here was found from this minus 1. So we'll take 2 minus the minus 1. So we get 0 minus 3 divided by 2 minus negative 1 to give us negative 1. And over here we take 9 minus 0 divided by 3 minus 0 to get the 3. And finally we take the 3 minus negative 1 divided by 3 minus negative 1 up here. Well, again, the most outer x values that you've used. So 3 minus negative 1 over 3 minus negative 1 is 1. How are we going to use that information? Well, we can start at the top, and we could say, well, the 0th degree polynomial through at least the first point is just y equals 0. The polynomial through the first 2 points is given by 0 plus 3 times x minus negative 1. So we just go down this diagonal. So we have 0 plus 3 times x minus negative 1. If we want the quadratic through the first 3 points, it's just 0 plus 3 times x minus negative 1 plus negative 1 times x minus negative 1 times x minus 0. And finally, we could get the cubic through these 4 points as 0 plus 3 times x minus negative 1 plus negative 1 times x minus negative 1 times x plus 1 times x minus negative 1 times x times 2 times x minus 2. That's 1 times x minus negative 1, x minus 2. And we've written them out over here. There's nothing special about going from the top. One can also go from the bottom and also get the cubic polynomial as y equals 12 plus 9 times x minus 3. Now we use the bottom, plus 3 times x minus 3 times x minus 2 plus 1 times x minus 3 times x minus 2 times x minus 0. The order that we list the points in doesn't matter. We didn't have to list the points from the lowest to highest or highest to lowest. We can mix them up and we'd still get the same polynomial. So the order doesn't matter. And if we added another point, well, then the other values that we've gotten in the table will still be fine, and we just have to find another entry in each of our columns, and then we'd have one more column to build up the fourth degree polynomial. A moment of culture. There was a social worker, a minister, and a computer scientist who all went out to play a friendly game of golf one day. At the course, they found a long line waiting to get to the first tee, so they asked the group in front of them what the problem was, and they were told that a group of blind golfers was on the course ahead of them. The following conversation ensued. The social worker said, "Isn't it wonderful what disabled people can do? If you only give them half a chance, they could do amazing things." The minister said, "It certainly is, but those golfers aren't on the course alone. The Lord helps those who help themselves." Finally, the computer scientist spoke up and said, "Yeah, it's neat all right, but why can't they play at night?" I'm Bruce Bouquet from the New Jersey Institute of Technology. Thanks for joining us, and may the power of math be with you.